back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. Well, in this hour, once again, we're going to throw the lines open because it's open mic. So let's take the first listener phone call.
John Thibodeau, Baton Rouge, Louisiana. Don't have the call letters. Can a black hole actually be just a rift in time? And that's what we're seeing, time distorted? Thank you.
Well, you're absolutely right. We think that a black hole is, in some sense, a rip in time. So let me explain. Let's say I have a trampoline net, and I put a shot put in the middle of the trampoline net. The trampoline net does not rip, but, of course, the ball descends and sinks into the trampoline net. And then if I get a marble and I fling the marble around the shot put, it'll orbit. It'll actually orbit around the shot put. Now, that marble is actually the Earth, and that shot put is the sun, and the trampoline net is empty space. So we have another way of looking at why the Earth goes around the sun. Why does the Earth go around the sun? Not because gravity pulls on the Earth. That's what Newton would say. Einstein would say, no. Space pushes. That's why we go around the sun. And why are you sitting in your chair today? You're sitting in your chair not because gravity is pulling you down into the chair. No. You're sitting in your chair today because the space above your head is pushing you down into the chair. And so this is a completely new way of looking at space and time. So if you want to summarize Einstein's general theory of relativity in one simple phrase, it is that gravity does not pull, space pushes. And then the question is, what happens if the shot put gets so heavy that it actually begins to tear the fabric of space and time? And that's what a black hole is. It is a rip in the fabric of time. But then the next question is, well, what happens afterwards? What happens if you throw a marble into the black hole itself, into the rip? Where does the marble go? Well, the short answer is we don't know. Now, we see black holes at the center of galaxies throughout the universe. If you want to see a black hole tonight, go outside in the night sky and look in the direction of the constellation Sagittarius. And in the area Sagittarius A, there is a raging black hole. Now, why can't you see it? Well, first of all, it's in the middle of a galactic nuclei, a cluster of stars that looks like a fireball. By rights, you should see a fireball brighter than the moon. A fireball brighter than the moon coming out every night. But you don't see it. Why? Dust clouds. Galactic dust. It turns out that the galaxy, the Milky Way galaxy, is quite dusty. In fact, that's where we come from. We are made out of galactic dust. But that's also the reason why you cannot see the center of the galaxy, and that's why you cannot see this fireball that rises every night, but you can't see it because of dust. Well, at the center of the fireball, there is a black hole. It weighs 2 to 3 million times the mass of our sun, so we know it's there. And we've even had pictures of stars being eaten up by this black hole. And perhaps maybe next year we'll have photographs of the center of this black hole. Surrounding the black hole, there's a sphere. The sphere is called the event horizon. It is a point of no return. If you fall into the sphere, you are going to be inevitably crushed at the center of a black hole. How? We don't really know. But we're lashing together several radio telescopes around the world to gain the resolution of a gigantic radio telescope the size of the Earth. Now, to build a radio telescope the size of the Earth is impossible. It would cost too much money. But by lashing together several smaller radio telescopes scattered around the surface of the Earth, and then combining the signal in a computer, we can recreate the image as seen by a radio telescope the size of the planet Earth. That telescope is so powerful that it can actually zero in on the event horizon. This is amazing. I never thought that in my lifetime I would be able to talk about photographing the event horizon of a black hole. That is the point of no return, a sphere that surrounds the black hole. We're going to have pictures of this perhaps as early as next year. Amazing, truly amazing. And then the big question is, what happens if you fall into the event horizon? Well, as I said before, we don't really know the answer. However, there's a Nobel Prize waiting for the enterprising scientist who figures out what lurks at the center of the event horizon. One possibility is that it's really a ring, not a dot, but a ring that rotates very fast, so fast it prevents you from falling through. Welcome back to Science Fantastic with Professor Michio Kaku. Keep the calls coming because the number to call is 612-564-8135. Well, before the break, we had a quick question about, does a black hole rip the fabric of space and time? The answer is yes, but how does it rip the fabric of space and time is still being debated by physicists today. All we can say is that surrounding a black hole, there's a sphere called the event horizon. And inside the sphere, perhaps there is a ring being the remnant of a rotating black hole. It collapses to not a ring, not a dot, but a ring. And if you fall through the ring, perhaps you fall through a gateway to another universe. That is still not verified. However, we see these black holes in outer space. You can see one tonight in the constellation Sagittarius. They're everywhere we see galaxies. Black holes working in the hearts of galaxies. Okay, let's move on to the next listener phone call.
Hello, my name is Robert Carretero. I'm calling from Miami, Florida. Listening to you on the internet. And my question is, now that NASA has discovered organic complex molecules on Mars and also methane, what steps are they going to be taking to see if they find some fossils or, determine how long ago life existed on Mars? Thank you.
Well, I was on the Fox channel being interviewed even before NASA made its announcement of organic chemicals found on Mars. And I was asked to make a prediction. What will NASA find with this Curiosity rover on the surface of Mars? And I said that, well, I hate to be a party pooper, but we're not going to find evidence of little green men. We're not going to find evidence of life, but we will find evidence of the precursors of life. Organic carbon-based molecules, organic molecules that will one day, if Mars had continued on its track, one day create perhaps the first DNA molecule. However, we didn't go that far. In other words, about 3.5 billion years ago, Mars lost its oceans. It lost its riverbeds, and it became a dead planet. Why? We're not sure, but we think that the solar wind blew the atmosphere of Mars away. Mars has no magnetic field to speak of to protect it. As a consequence, the solar wind blew much of the atmosphere into outer space and therefore lost most of its water in the process. So, are we going to find fossils? I don't think so. Are we going to find shells and skeletons? No, I don't think so. But will we find amino acids? And that, I think the answer is yes. When you crack open meteorites from outer space that landed on the Earth, many times you find amino acids. Amino acids are the precursors of proteins. You stack a bunch of amino acids together, and it creates proteins, and that's what we're made out of. For the most part, we are made out of proteins. So that's the next step. The next step is to keep on drilling into the Martian rock to find evidence of amino acids, perhaps maybe even a DNA molecule. That would be a real game changer. But to find life as we know it, I tend to doubt it. Mars is bleached by the sun. For all we can tell, it is a dead planet. However, we're now digging underground into the soil of Mars, and so maybe we'll find some surprises, maybe evidence of ancient microbial life. That, I think, is the maximum we can expect. We're not going to find little green men, but we may find evidence of ancient microbial life on Mars. Okay, well, let's move on to the next listener phone call.
My name is Madison Wolf. I'm from Yorksville, Ohio. And my question is, if time travel was possible given Einstein's equations, and, the details and workings behind that. Thank you.
Yes, Einstein proposed his general theory of relativity in 1915. And then around 1949, he was at Princeton, and his next-door neighbor there was Kurt Gödel, one of the greatest mathematicians of the century, in fact. And what Professor Gödel found was a new solution of Einstein's equation, which allowed for time travel. He assumed that the universe was rotating, and if the universe was rotating and you went around the universe, you would come back before you left. In other words, you would become a time traveler going backwards in time. Now, Einstein knew about this because, of course, that was his next-door neighbor at Princeton, and he was very disturbed. Einstein himself thought that his equations might allow for time travel, but he couldn't quite get himself to believe that was real. So in his memoirs, Einstein wrote that, quote, "We can dismiss these time travel solutions because they're not physical." In other words, the universe expands. We have a big bang, not a big swirl. We have a big bang, and the universe expands uniformly, doesn't rotate, but if it did rotate, then perhaps you could journey back into the past whenever you wanted. So in some sense, thank goodness we don't live in a rotating universe, because then all sorts of paradoxes could be formed. But then in 1963, Roy Kerr, a New Zealand mathematician, discovered another solution of Einstein's equation, which is even crazier than the Gödel solution. He found that black holes, that we mentioned before, rotate. Rotating black holes do not collapse to a dot, they collapse to a ring. If you fall through the ring, you wind up through a wormhole, which can also be a gateway into the past. Since then, we've discovered scores of solutions which allow for Einstein's equations to give us time travel. In fact, there are so many solutions that Stephen Hawking tried to catalog them. The late Stephen Hawking found a whole classification of time travel solutions in Einstein's equation, and he found a commonality between all of them. It turns out that what you need to create a time travel solution is negative energy. Energy that is less than zero. We don't see negative energy too often, but in the laboratory, we can actually make negative energy. That's the common factor among all these time travel solutions that Einstein found, negative energy. Now, negative energy would make possible not just time travel, but warp drive as well. Now, in Star Trek, the Starship Enterprise, the crew there, tries to find dilithium crystals. Dilithium crystals are the engine that makes the warp drive possible and maybe even time travel. But of course, dilithium crystals don't exist. That was the figment of the imagination of Gene Roddenberry, the creator of Star Trek. But in the physics laboratory, yes, we have a counterpart of dilithium crystals called negative energy. However, what's the catch? There's always a catch someplace. You need fabulous amounts of negative energy to stabilize a black hole. First of all, you need a black hole to open a gateway through space and time, but the gateway is not stable. Then you need negative energy to stabilize the gateway so it doesn't collapse on itself. So here we are. Today we realize that there are scores of solutions of Einstein's equations which allow for time travel. And according to Stephen Hawking, the commonality is that you need negative energy to keep the gateway open to the past so that you don't get crushed by the black hole as you enter the gateway. So what does it mean for us? In the short term, nothing. because the energy necessary to open up the gateway is that of a black hole, and don't expect anyone to play with a black hole anytime soon. This is really for a very advanced civilization, perhaps a Type 3 civilization, a civilization that has galactic power, that could, therefore, use Einstein's equations to go into the past. That is something we cannot rule out. Okay, well, let's move on to the next listener phone call.
Hey, this is Brandon from Manhattan, and I was wondering, do you believe that it's possible that cannabis kills cancer cells? I know that there's thousands of cancers, that's what you said, but you think it's possible that cannabis can slow down or even kill cancer cells? Thank you very much.
Okay, well, let's take a short commercial break, and after the break, we'll talk about cancer and what is known and not known about how to kill cancer cells. Welcome back to Science Fantastic with Professor Michio Kaku, and let's move on to the first listener phone call.
Hi, this is Vlad. I'm calling you from San Francisco. I have a question on the specificity around mankind's ability to pull out of the climate crisis and growth as it pertains to carbon emissions and rapid polar caps melting. Thank you.
Well, let me answer that, and then I'll answer a previous comment that was asked by a listener concerning cancer. First of all, let me say that there are no simple technical fixes to the climate problem. First of all, if you're a farmer, you know that the atmosphere and the weather is changing. Summer times are about a week longer than in the past. Winters are about a week shorter. And if you go further north into Canada and Alaska, you know that, well, the glaciers are receding and tundra is thawing out. In fact, I was in Siberia a few years ago speaking there, and yes, they tell me that the tundra of Siberia is thawing out. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had several phone calls. One phone call concerned global warming. First of all, the atmosphere is changing. The weather is changing. Farmers notice this. People in the forest notice this because animals are very sensitive to the cycle of the seasons, when to hibernate, when to search for food. All these cycles are being disrupted. And if you are a forester, you know this. If you live in Alaska or Canada or Siberia, you know that, yes, the tundra is thawing out. In fact, when I spoke in Siberia, people there told me that because the glaciers are receding in Siberia, it means that ancient animals, carcasses, ancient animals that died tens of thousands of years ago, are now re-emerging because the ice is melting. And just realize that these animals died tens of thousands of years ago, and yet their bodies are only now being recovered by scientists because the ice is melting. And the people of Siberia in Krasnoyarsk, where I spoke, told me that they actually like it. They actually like it because, hey, who wants to be bound in ice all the time? Why not have a little bit of sunshine? Well, a little bit of sunshine there means weather changes elsewhere on the planet Earth. What's good for some people in some areas may not be so good in other areas. For example, the South Pole is beginning to slowly disintegrate. No one's talking about the complete collapse of the South Pole, but gigantic chunks of the South Pole are in fact breaking off. So what are we going to do about it? Several things could happen. First of all, technical fixes are possible, but are a long shot. some people think that perhaps we can grow genetically modified plants that love carbon dioxide that'll soak up the extra carbon dioxide. Well, yeah, but so far no one's done it yet. Some people think we can shoot soot into the atmosphere to blanket out sunlight and darken the earth as a consequence with soot. But hey, if you put soot in the air, sooner or later it comes back down, and it could wind up in your children's lungs, and who wants that to happen? So a number of technical fixes have been proposed, none of them being very reliable. They're very easy to pick apart, they're very expensive, and they have unforeseen consequences. For example, seeding the oceans with iron is one way to increase algae activity, but it could get out of control as well, and all of a sudden you can ruin the delicate balance between algae and fish and sea life by putting too much iron-based chemicals into the oceans. However, there is some good news. One of the good news is that the solar revolution will be jump-started by cheap batteries. One of the reasons why we don't have a solar revolution is because solar power is not very economical, because at night you're wasting all that time that you could be gathering sunlight, but the sun has set. What you want is a battery, a super battery that can have efficient storage of electricity when the winds don't blow and the sun doesn't shine. And Elon Musk has even bet the store. Tesla Motors has spun off a division whereby they're going to make super batteries, which they hope will change the balance of power in your pocketbook, making it economically viable to go with solar technology. And that is a bright side on the whole question. And then another possibility is fusion power. Fusion power is a long ways away. We're talking about perhaps mid-century before it becomes economically viable. However, scientists do believe that one day fusion power could perhaps solve the whole problem of global warming, because fusion power will give us the power of the sun using seawater. Seawater is the basic fuel for fusion engines because they burn the hydrogen inside seawater, and that could be a solution. I should also point out that we had a previous caller who asked about cancer research, and let me just say a few words about cancer research. First of all, there are three ways to approach cancer. You can use surgery to cut it out, radiation to zap it, and chemotherapy to poison it. All three are unpleasant. They have side effects. However, there's a new technology out there that could give us a new handle on it, and I'll talk about that after the break. So let's take a short commercial break, and after the break I'll talk about breakthroughs in cancer research and cancer therapy. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open because it's open mic in this hour. Well, before the break, we had a question about cancer research. Let me just summarize some of the things that we mentioned here on Science Fantastic. First of all, immunotherapy has now been added to our arsenal against cancer. Immunotherapy basically takes some of your immune cells out of your body, for example, in blood, and then genetically modifies them so they can identify and hunt down cancer cells, and then you re-inject it back into the body. Well, the results have been incredible, fantastic. Many people that were considered terminal, that were doomed to die of cancer, have come back from the dead in some sense, and they have lived to tell about it. Now, there are side effects. In fact, some of the side effects are pretty severe. But some people say it's worth the effort to try because these people are terminal. Scientists have written them off. They are going to die. So why not give them immunotherapy? So that's one more weapon that we have. And another weapon is nanotechnology. We can now create nanoparticles that zoom in on individual cancer cells and zap them. We can zap them by having small amounts of poison on the nanoparticle. The nanoparticle zooms in on cancer and delivers microscopic quantities of poison. Not huge amounts like in chemotherapy, but microscopic amounts of poison right on the cancer cell. Another form of nanotechnology is vibration. We can actually create nanoparticles that vibrate on demand. They home in on a cancer cell. Then we vibrate them to rupture the cell wall. This is called nanotechnology or nanomedicine, and that is yet another way in which we can attack cancer. So we just don't cut, zap, and poison cancer. We can now use our own body's defenses, augment them, and use our own body to create cancer cell destroying cells that allow us to cure some forms of cancer. So there is some hope on the horizon, even for fatal forms of cancer. Okay, let's move on now to the next listener phone call.
Hello, this is Colton, and I'm from Kennewick, and I was wondering how black holes can go into gray instead of black, like Dr. Einstein, I'm pretty sure, said that it can go grayish, blackish. I was wondering how the vortex can suck stuff in, and you can get out with thrusters instead of with an astronaut suit. Thank you. Have a nice day. Bye.
Okay, well, you asked some questions that are at the cutting edge of research. First of all, my colleague, Stephen Hawking, who recently passed away, he was the one who showed that black holes are not totally black, but they're actually gray. Now, let me explain. First of all, why are black holes black anyway? Because light itself cannot escape from a black hole. The black hole's mass is so great that even light cannot escape. For example, you know that if you throw a rock in the air, eventually the rock comes to a halt and comes back to Earth. If you throw that rock fast enough, if you hit 25,000 miles per hour, the escape velocity of the Earth, that rock will escape the gravity of the Earth and leave the Earth forever. So the escape velocity of the Earth is 25,000 miles per hour. That's the velocity you have to go to reach the moon. If you want to jump and reach the moon, jump 25,000 miles per hour, and you too can reach the moon. Now, stars also have an escape velocity. The escape velocity of a gigantic star is the speed of light. Since nothing can go faster than the speed of light, it means that nothing can escape a black hole. That's why they're black, because nothing can escape, not even light. However, if it's pure black, that violates the uncertainty principle of Heisenberg. Believe it or not, Werner Heisenberg, the greatest quantum physicist of his era, showed that there's always uncertainty. There's never anything that is perfect. Therefore, there's no such thing as perfect black. There's no such thing as knowing perfectly the velocity of an electron or the position of an electron. Everything is uncertain. Even blackness is uncertain. And so blackness becomes gray. And what comes out? A very soft radiation comes out of a black hole called Hawking radiation, named after Professor Hawking. So he was the one who showed that when you apply quantum mechanics, that is the theory of the atom, to black holes, which are based on Einstein's theory of the universe, then you find that black holes are not totally black. They're actually slightly grayish. That's why, by the way, he never won the Nobel Prize. This radiation is very faint, and that's why it's never been observed, and that's why Stephen never won the Nobel Prize. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And this hour, the lines are open. Okay, well, let's move on to the next listener phone call.
Hi, my name is Nick Rudolph. I'm calling from Phoenix, Arizona. The station is KJVV. And my question is, do you have any suggestions for teaching young people, small kids, or actually even adults, how to think more like a scientist instead of just what to think? How to get them to think more critically and develop their own ideas opposed to just regurgitating repetitive things that they've been reading. Thanks.
Wow. You asked the $64,000 question. If we knew the answer to that, if we could somehow bottle it, we could change human society. It's difficult because, of course, we have to separate form and content. Most of us react to form and appearances. Very rarely do we ask why, how. Very rarely do we go deeper into something. But that's what science is all about. Science is all about trying to understand Mother Nature, trying to understand the principles and concepts behind Mother Nature. But, as you pointed out, unfortunately, people get bogged down in memorization. So I tell science teachers that I sometimes meet that, well, yes, you got to memorize some things. After all, you just can't glide by sciences BSing things. You have to know some facts. But beyond that, you have to organize the facts into a concept, a principle, a picture. And that's what separates the Einsteins of the world from simply somebody who is a tape recorder. That is, you have to ask why. You have to ask how. In other words, there is a principle behind all the scattered pieces of data. When you read a book about biology, oftentimes you get lost in all the parts of a flower, the anatomy of a human being. You get lost because there's so much out there. But if you were to ask, what is the principle that drives these things, then you realize that there's only a handful of principles, concepts that drives the whole thing. And then there's a picture that allows you to very quickly summarize the essence of what's happening. For example, with relativity, the picture there was, well, given to us by clocks and meter sticks and by trampoline nets, things you can visualize that were distorted as you go to higher velocities and higher energies. And even Newton's laws of gravity can be summarized in a picture of balls going around other balls, about balls colliding with other balls. You can summarize all the laws of mechanics into a simple physical picture. So that's why I stress to people, especially science teachers, that they really should stress concepts and principles, not just memorizing dry facts and figures. And then science teachers ask me another question. How do you inspire a young kid? Well, my personal point of view is that we are all born scientists. All of us are born asking, why does the sun shine? Where did we come from? We're born asking these questions. And then we hit the greatest killer of scientists known to science. We destroy young scientists by the millions every day. The greatest killer of scientists is junior high school. That's right. When you hit the danger years, when you hit 13, 14, 15, you're in junior high school, that's when we lose young scientists by the millions. Because science is reduced to memorization, people are distracted, science is not made interesting, because of course we're competing against all the distractions of junior high school. That's when we lose scientists by the millions. And we have to inspire them. We need role models for young scientists. We need breakthroughs that inspire them, like a Sputnik moment or the landing on the moon. We need things that encourage them, like parental guidance, teacher guidance, mentoring. These are the things that we need to make young scientists. Okay, well, let's move on to the next listener phone call.
Hello, this is Frank in Columbus, Ohio. And my question is about the supermassive black hole at the heart of the Milky Way. Sagittarius A has a solar mass of about 4 million solar masses. Now, it is the center of the Milky Way galaxy. It should be the center of the mass. But there are billions of stars in the galaxy. And I've seen an estimate that the Milky Way has an overall mass of 700 billion solar masses. So how can something 4 million with 4 million solar masses be the anchor for the entire Milky Way? It does not seem to be massive enough. What's up with that, Professor? Thanks.
Well, you ask a very important question that is bedeviling astronomers even today. First of all, we have the galaxy, a gigantic swirling disk of stars, many of them containing 100 billion, or many times that, 100 billion stars in a gigantic flying saucer-shaped disk that rotates. And then at the very center of the galaxy, we find a black hole. A black hole that does not weigh billions of times the mass of the sun, but millions of times the mass of the sun. And then the question is, which came first? And the answer is, we don't know which came first. There's an active debate going on right now. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a question about black holes. You see, the black hole at the center of the Milky Way galaxy weighs a few million times the mass of the sun. But the galaxy itself weighs billions of times more, hundreds of billions of times more. And so the question is, how is it possible that a teeny-weeny black hole can whip around the entire galaxy, which weighs many times more than the black hole itself? Well, the reason is actually rather complicated. First of all, we have to understand where both came from. Which came first, the chicken or the egg? Did the black hole come first, or did the galaxy come first? Well, the short answer is we don't know. It's a raging debate in astronomical circles even now. Let's say the black hole came first. If the black hole came first, then it's like the moon going around the Earth. The moon is much bigger. No, the Earth is much bigger than the moon, of course. But why is it, therefore, that the black hole at the center of the universe is so much smaller than the rest of the galaxy? So if the black hole came first, the black hole should be bigger, but it's not. The other possibility is valid. Maybe the galaxy came first, and a small piece of it then condensed into the black hole. Now, my personal point of view is that they were both formed at the same time. And that would answer your question. If the Earth is much bigger than our moon, then why isn't the black hole much bigger than the galaxy? Because the galaxy spins around the black hole. And the answer is as follows. First of all, the black hole at the center of the galaxy does not whip around the rest of the galaxy. As you correctly pointed out, the galaxy weighs many times more than the black hole itself, and the black hole is rather tiny in comparison with the galaxy. But if they formed together, it means that they were whipping around each other so that we see the galaxies of today being so much bigger than the mass of the black hole at the center, because they were both formed at the same time. Well, the short answer is we don't know for sure. There's a raging debate in astronomical circles as to which came first, the chicken or the egg, the galaxy or the black hole. But if they both formed at the same time, that would then answer the question, why is one so much bigger than the other? Okay, let's move on to the next listener phone call.
Hi, this is Ben in Chicago. I'd like to know, Dr. Kaku, if it's theoretically possible for an advanced civilization to be able to override nature and change the laws of physics itself to serve their own purposes, or to create their own custom-made universe with a superior set of natural laws, and then to transport their civilization there. Thank you.
Well, this actually was a big theological debate 1,000 years ago in the Muslim world. You realize that 500 to 1,000 years ago, the Islamic people were actually more advanced than the Europeans. The Europeans during the Dark Ages were engulfed with the Inquisition. They burned witches. They burned warlocks. Look what happened to Galileo. Giordano Bruno was burned alive in the streets of Rome. So Europe was not a very pretty place to be, but science flourished in the Islamic Empire. But there was a debate 1,000 years ago precisely on that question. There were two sides to the question in the Islamic world about 1,000 years ago. The scientists at that time said that natural law is going to be more or less the same everywhere because that's the way Allah created it. So therefore we should study natural law. However, the people who are very religious, the theologians, said no. You see, Allah can change natural law anytime He feels like. He is beyond natural law. Therefore, natural law should not be studied. Why bother to study something that can be changed at will on a whim by Allah? Well, it turns out that the religious people eventually went out, and science in the Islamic world about 500 years ago began to stagnate, and the Islamic world fell backwards with regards to the Renaissance, where science began to flourish. So the whole question of the fall of the early Islamic Empire hinged upon the question, is natural law always the same, or can the Creator simply change it on a whim? In which case, why bother to learn about it, because it's going to be changed anyway. Well, now we have a different twist on it. We have something called string theory, which we think, though we cannot yet prove, is the theory of everything. It's what I do for a living. In fact, I'm the co-founder of string field theory, one of the main branches of string theory. And string theory gives us not one universe, but many universes. So if I think of a bubble bath, each bubble representing a universe that's expanding or contracting, then the bubble bath of universes is called the multiverse. Now, where does physics come into picture? Each bubble is a solution of the string equations, but there are more than one solution. In fact, there could be an infinite number of possible solutions. This gives us a multiverse. And do the laws of physics change between universes? Yes. Each bubble has a slightly different version of the laws of physics. Now, there is a metaphysics, a physics beyond ordinary physics, and that is string theory. So string theory would be the physics of all universes. All possible universes would obey the string equations. But each individual universe can be different from any other neighboring universe. This means that in some sense, yes, there could be other laws of physics. Now, how do you prove this? Well, one day we're going to launch LISA into orbit, and LISA is the Laser Interferometry Space Antenna, which detects gravity waves in outer space. Now, gravity waves were detected recently, winning the Nobel Prize to 3 physicists recently. So we know that gravity waves exist when black holes collide. But at the beginning of the universe, the shock wave from creation itself created a gravity wave that is still detectable even today. And one day we'll get baby pictures of the infant universe as it's being created, as photographed by LISA. And we hope to find evidence of an umbilical cord connecting our baby universe to a parent universe, with both universes having a slightly different laws of physics. So you're absolutely right. This idea that the laws of physics can change is actually one of the dominant theories in cosmology today. Okay, well, let's move on to the next listener phone call.
My name is Cecil from Knoxville, Tennessee. My question, Dr. Kaku, is, have you looked at the Edgar Cayce materials, the psychic Edgar Cayce materials, on our three-dimensional reality as a projection from the fourth dimension, the spiritual dimension? This is similar to your multiverse, I think. Thank you very much, Doctor.
Well, you're right that Mr. Cayce was a person who some people believe was a prophet who could predict the future. However, in physics, we have something called causality, and causality says that cause and effect is one of the basic fundamental structures of our universe, and cause and effect mean that causality is not violated, so you cannot see the future. Now, that doesn't mean that you can't play with Einstein's equations. It just means that the average person sitting on the planet Earth is not going to be able to see the future at any time soon. However, as you also pointed out, some people who are psychics have looked at the idea of ghosts, spirits. And they say that in some sense, perhaps our universe is a sliver or a shadow of a much larger universe where ghosts can exist. This idea was actually popular around 1900. Around that time, a theologian wrote the book Flatland, which captured the imagination of Victorian England because it mentioned the fact that there could be other universes. Our universe could be flat compared to a higher dimensional universe, and ghosts could live there. Well, we'll talk about ghosts after the break. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in science, and in this hour, we're throwing the lines open so that you can be part of Science Fantastic. Let's take the next listener phone call.
Hi, my name's John. I'm calling from Harrisburg, Pennsylvania. I listen to your program on the Internet, and I just had a question about, it has to do with camera technology as far as we're at 4K now, and I was wondering if we'll be seeing 8K and where camera technology might be going in the next couple of years. Thank you, and I'll continue to listen.
Well, it's hard to predict because, of course, we have Moore's Law. Computer power doubles every 18 months, which means that the way in which we process visual images can be vastly increased by simply increasing the computer power that we have in our central processor. Also, however, there are limits. There are limits to what we can do with images, and these limits are given to us by quantum mechanics. For example, if you have a Pentium chip that has layers of silicon and insulators, these layers can be about 20 atoms across. But in 5, 10, 20 years, it could be 5 atoms across, in which case you get leakage taking place and heat generation, which will destroy you. So, in other words, there are limits to what you can do even with computer technology. There's also the fact that every pixel of an image, there's a transistor. And so the number of pixels that you can put in a digitized photograph is a function of the size of the transistor. And the size of the transistor, in turn, is once again determined by quantum mechanics. It's hard to get a transistor smaller than 1 atom, for example. Now, with nanotechnology, we can now create substances like graphene that are 1 atom thick, made out of carbon, a sheet of carbon 1 atom thick, and it turns out that you can take a transistor, make a transistor out of a single atom. So the smallest possible transistor that we've been able to make so far is the size of a single atom, an atom of graphene, which is a single layer of carbon. But that's a limit. So in other words, this is not going to go on forever. We're not going to reach that quantum limit for quite a while. So for quite a while, we will be able to get better and better resolution. But there is a limit. It can't go on forever. Oh, by the way, another thing. A previous caller asked about, well, to put it bluntly, ghosts. Because people like Edwin Casey talked about other universes, and these ideas are being revived in physics. As I mentioned earlier, in 1900, theologians were asked the question, where is heaven? We had telescopes in 1900 that were very powerful, and no matter where we looked, we could not find heaven. So this was very embarrassing for theologians. And then in mathematics, the idea of higher dimensions became quite popular. So theologians said, aha, we have the answer. Heaven is in hyperspace. And if you have the power of hyperspace, you can move through walls. You can do the power that is normally ascribed to ghosts. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a question about 3 dimensions and 4 dimensions, and let me explain what all that is about. Back in 1900, as I mentioned, theologians had a problem. Telescopes were becoming very powerful. Everywhere they looked in the skies, they could not find heaven. Where is heaven? Well, around that time, mathematicians were looking at higher dimensional spaces. We live in 3 dimensions, length, width, and height. 4 dimensions don't seem to be in the cards. Where is the 4th dimension? We cannot see it, feel it, doesn't seem to exist. Now, Einstein said that the 4th dimension is time. Okay, but where is then the 5th dimension? Where are these higher dimensions? And around 1900, theologians read books on mathematics, and these mathematicians seem to indicate that if you lived in a higher dimensional world, you would have the power of a ghost. That is, you'd be able to walk through walls. Walls are not a problem because you simply hop over the wall by going into the 3rd dimension. And so many people said, aha, that's it. That's where ghosts are. And people like Edwin Casey picked up on it and said, perhaps we live in a 3-dimensional projection of a 4-dimensional world where ghosts exist. Ghosts can disappear, reappear, walk through walls, and that's exactly what a hyperdimensional person can do looking down on our puny 3-dimensional world. Well, that theory never got anywhere. Why? Because there was no experimental evidence that pushed our understanding any farther. Now we have string theory. String theory has not yet been proven. It's a subject of considerable controversy, in fact, but string theory can only exist in 11-dimensional hyperspace. So we have this problem. The theory of all theories, the end of all theories, the final theory could be a theory existing in higher dimensions, but we need more powerful instruments to prove it. So go to my book, Physics of the Impossible and Parallel Worlds, where I have a discussion of how you can test the ultimate theory of all theories, a theory which makes possible higher dimension, and if you are a mystic, it makes possible ghosts. Okay, well, let's move on to the next listener phone call.
Hi, this is Armand again from Queens, New York. I listen to you on YouTube, and I was wondering, when do you think we're going to have the first Iron Man suit that functions like the one in the movie? And how possible do you think it is to create a lightsaber that works like in Star Wars? Thank you very much. Have a great one. I love your show. Peace.
Okay, well, you ask a fair question. First of all, the United States military has dumped over $150 million to create the Iron Man exoskeleton. We have all these GIs from Afghanistan and Iraq with damaged spinal cords who are paralyzed, quadriplegic. So far, the most advanced exoskeleton is based at Duke University, made by Dr. Nikolilis, who I've actually had on Science Fantastic. His dream was to create an exoskeleton that would allow a quadriplegic to kick the football, initiating the World Soccer Games in Sao Paulo, Brazil. Well, he succeeded. 1 billion people tuned in and saw a paralyzed person put on a suit that allowed him to kick the football, initiating the World Cup soccer games. Now, That is a far cry from the Iron Man suit of the comics. That suit allows you to fire missiles, travel at supersonic velocities, practically go into outer space. We're not there yet. We can just barely make a suit that allows the mind to kick a football, initiating the World Soccer Games. Well, after that, I'll say a few things about lifesavers as well. Once again, you are listening to Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. In Science Fantastic, we have an open mic. That is, you can get to the phones and give us a call and have your thoughts heard on national radio. Well, before the break, we had a call about the Iron Man costume. We are decades away from creating an Iron Man costume that can fire missiles, that can launch a human at supersonic velocities, and do all the wondrous things that is found in the comic books. Sorry about that. The best we can do after spending $150 million is to connect the living brain of a paralyzed person directly to a suit that allows this person to walk and kick a football. You know, Christopher Reeve, the handsome actor who plays Superman in the Superman movies, he died, but he was involved in a tragic accident whereby his spinal cord was severed in an accident involving a horse. Very, very sad. But his dream was to be able to walk again, and that's what we can do at the present time. He didn't live long enough to see that, yes, it is possible for someone who's totally paralyzed to walk. But that's a far cry from having an Iron Man costume. And then lightsabers are also possible, but not quite the way you see in the movies. First of all, a lightsaber is supposed to be a column of light that terminates. Well, as you know, light does not terminate. It keeps on going. However, the closest you can get to the idea of a lightsaber that can cut through wood and steel is a plasma torch. So, I once hosted a series for BBC and the Science Channel called Sci-Fi Science. And in Sci-Fi Science, I actually go through the stages of building a plasma torch. In fact, I built a crude plasma torch on TV for the TV audience. Now, of course, it's not the real thing, because the real thing, of course, terminates. And here you have a plasma torch that has a spine to it. It is not nothingness connected to a lightsaber. No, it has a spine, and out of the spine comes a stream of hot plasma sufficient to slice through wood and different kinds of objects. So it's not quite the Star Wars lightsaber, but it's about as close as you can get with known technology. Okay, well, let's move on to the next listener phone call.
Hi, this is Jack from San Francisco, California. I'm calling in to listen line, and my question is around the super force, or we can look at it as the human force as it pertains to the consciousness, and how consciousness, if it affects at all the four forces: gravity, electromagnetism, strong nuclear, and weak nuclear. So I wanted to know how our consciousness plays a factor into the super force, and how that gets affected.
Okay, well, let me try to break that down into its components. First of all, there are four fundamental forces that we know about. First is gravity, which keeps us anchored to the floor and holds the sun together. Without gravity, the solar system would fly apart and the sun would explode. So we need gravity. Next is light, electromagnetism that lights up our cities. Fire, for example, is an example of electromagnetism. So that is the electromagnetic force. Then we have the two nuclear forces, the weak and the strong nuclear force, which, for example, makes possible the sun, makes possible nuclear weapons, makes possible nuclear power plants, and gives us radiation, gives us the elements of uranium and the transuranic elements. So that's the nuclear force. However, we've looked for a fifth force. We've tried very hard to find a fifth force, and so far, nobody has yet succeeded. Science is based on things that are testable, reproducible, and falsifiable. Now, what about consciousness? Well, it turns out that we scientists can augment the power of the mind, connecting the mind directly to a computer, and then having the computer do all sorts of magical things. For example, telepathy. For example, psychokinesis or telekinesis, moving objects with the mind. We can actually do that now. For example, on a simple scale, it turns out a quadriplegic, hook up the quadriplegic with a chip in his brain, and have him able to surf the web. He can turn on the lights, turn off the lights, turn on his wheelchair, and anything you can do with electricity, he can also do with the power of the mind connected to an electric generator. Now, that's not quite the consciousness you see in science fiction movies, but it is a direct connection between the human mind and a computer. Now, in the future, it means that we'll have some form of telepathy and a brain net whereby thoughts, emotions, feelings will be sent on the internet, and also allowing you to control machines. So just like in Harry Potter, you'll have the ability to move objects because your mind will be connected to a computer, and the computer in turn will be connected to a machine which can move mechanical objects and do many of the dazzling feats you see in the science fiction movies. But this is called synthetic telepathy. But telepathy without enhancement, we have tried to do and have been unsuccessful. The human brain by itself does not have these magical powers. Okay, well, unfortunately, that's it for Science Fantastic.